In today's lesson, we're going to finish off big idea number 4 and talk about complete and incomplete combustions. As well, by the end of the lesson, you should be able to describe reactions as being endothermic or exothermic and explain why those reactions occur. Combustion reactions are when you burn something in oxygen gas. There are two different kinds based on how much oxygen is added. A complete combustion occurs when you burn a substance with extra oxygen present. We often describe the combustion reactions of hydrocarbons. These are chemicals that only contain H's and C's. When they do complete combustions, the products formed are water and carbon dioxide. Here's an example. Butane, which is found in cigarette and barbecue lighters, is the formula C4H10. If burned in lots of oxygen, you'll just make carbon dioxide and water. Notice the state of water here. It's a gas. This is because in combustion reactions, there's lots of heat around, which will boil the water. I always think about it this way. When I'm barbecuing, I get steam rising up instead of water, liquid water, puddling in the bottom of my barbecue and falling on the ground. Other substances can do complete combustion reactions as well. The definition of a combustion reaction is you burn something and make a stable oxide. Here's an example that we did in the lab. When you burn magnesium, you react it with oxygen and make magnesium oxide. Typically, we describe this as a synthesis reaction because it's two elements becoming one compound. But because I'm burning something in oxygen, this can also be classified as a combustion. If you're looking at a combustion reaction, you know it's complete if your flame is blue in color, and it's also described as being clean. So, no smoke, very little ash, no soot remaining. Complete combustion reactions also release the maximum amount of heat for the amount of fuel that you're burning. Incomplete combustions often involve hydrocarbons as well. They occur when you have not enough oxygen mixed into your reaction. Visually, you can see this by an orange or yellow flame that's often dirty, meaning there's lots of smoke and you sometimes see lots of ash and soot made. Because there's not enough oxygen present, not all of the carbon in the hydrocarbon gets changed to carbon dioxide. Some of it only is able to bond to one oxygen, or when the oxygen runs out completely, none at all. So in a complete combustion, you make 4 products. You make carbon dioxide, water, and when the oxygen starts running out, you make carbon monoxide, and when there's absolutely no oxygen left, solid carbon. Incomplete combustions can be very dangerous because carbon monoxide, CO, is a poisonous, tasteless, odorless gas that's actually fatal to humans. This is why houses need to have carbon monoxide detectors. If your house begins to fill up with carbon monoxide because there's something wrong with your furnace and you get an incomplete combustion going on, the signs and symptoms of being poisoned by CO are you feel tired, dizzy, nauseous, and you just want to go to sleep. The problem is, you never wake up. For incomplete combustions, there's always more than one way to balance the equation. See, in my example I have 8 Cs. I decided to balance it by putting a 2 in front of the carbon dioxide and a 5 in front of the solid carbon. I could have balanced this a different way by putting a 6 in front of the CO2 and left the CO and the carbons as 1. It doesn't matter which way you balance it, as long as you get your equation so that the number of atoms on both sides are the same. After you watch the videos on endo and exothermic reactions, here's some homework practice on complete and incomplete reactions, recognizing them and completing the balanced chemical equations for them. When you've done labs before and mixed chemicals together, you might have noticed that your beaker felt hot afterwards, or even, for some reactions, cold. This is because reactions can release heat or require heat in order to occur. A different classification, other than the synthesis decomp single-double that we've been using, is by classifying reactions by their thermic energy. The way this works is there's always a balancing act in terms of energy on the left side of the equation and the right side of the equation. Whenever a bond or an intermolecular force is made, energy is released because particles get trapped and need to slow down. So it makes sense that the opposite would occur as well. Whenever a bond or an intermolecular force is broken, that same amount of energy is required or absorbed by the atoms. In a reaction, there's often an imbalance between the amount of energy required to break the bonds in the reactants and the amount of energy released when forming the bonds in the products. Here's a hypothetical example. Let's say, for example, I'm doing a combustion reaction with CH4. If I'm burning this with oxygen gas, if I supply this reaction with lots of oxygen and do a complete combustion reaction, I'll just make some carbon dioxide and some water. Now, in order for this reaction to happen, I need to break each of the bonds in the reactants so that my atoms are free to move around. Each specific bond has a unique energy requirement to break. Let's say, for example, it takes 5 energy units to break the bond between a C and an H. In my CH4, I would need to break 4 CH bonds. That would be 4 times 5 energy units, so it would cost me 20 units of energy to destroy my CH4. Now, an O to O bond requires a different unique energy amount. Let's say, for example, to separate these 2 oxygens, it takes 12 energy units. So total, to destroy the bonds in my reactants, I would need 32 energy units. Now, when I form the bonds in the products, this releases energy because I'm making new bonds. Let's say, for example, whenever I make a CO bond, it releases 15 energy units. Because I'm making a CO bond here and a CO bond here, that would get me 30 energy units to make a CO2. And still, when I make my water, I get a different amount of energy out. Let's say, for example, when I make an OH bond, I get 20 energy units out. For every water, I have to make 2 of those, so that gives me 40 units. Therefore, total energy released in forming my products would be 70. There is always an imbalance between the energy that's required to break the bonds in the reactants and the energy released making the bonds in the products. Notice that less energy is used to destroy my reactants than to make my products. Therefore, there'll be extra energy coming out of this reaction. In this example, doing a complete combustion of CH4 will release energy. The difference between 70 energy units and 32, well, that's 38 energy units released. Notice that there's more energy on the product side than there is on the reactant side. Because my energy is being released, it means that when I touch the reaction, it will feel hot. This is the definition of an exothermic change or an exothermic reaction. You need to memorize this definition. The definitions for exo and endo get confused a lot because they're a little wordy and they're almost exactly the same. In an exothermic reaction, the energy released making the products is greater than the energy required to break the bonds in the reactants. Therefore, there's extra energy on the product side. This extra energy is released as heat into the environment, so it feels hot to the touch. So here are some examples. When you burn a candle, it feels hot. When you burn gasoline, and this is an interesting one here, when you have water freezing into ice. Remember, whenever bonds are made, it releases energy. So when water molecules get locked into an ice crystal, they're held together by hydrogen bonds. The energy released from hydrogen bond formation makes freezing water exothermic. This is why, in order to change water into ice, you have to remove the heat and put the water in the freezer. Endothermic reactions are the opposite process. The energy required to break the bonds in the reactants is greater than the energy released in making the bonds in the products. This means that our chemicals require energy in order for the reaction to happen. This extra energy that's needed is taken from the surroundings, and that includes you when you're touching your beaker. Because energy is being stolen from you, it means that it feels cold. Two examples of this are melting ice. In order for ice to turn into water, heat must be added to break the hydrogen bonds to separate the water molecules. Another example are chemical cold packs. You've probably seen them in the drugstore, where it's a plastic pouch and there's a liquid inside and you twist it and it pops and you shake it. When you do that, you're mixing two chemicals together. When they react, the energy required to break the bonds in the reactants is pretty big. So the chemicals steal heat from the environment, including you, in order for the reaction to occur. So what kind of questions should you be able to answer based on endothermic and exothermic reactions? First of all, you should be able to identify whether an example is endo or exo. Does the process release heat, or does it require heat in order to occur? Secondly, if I tell you that a reaction is endothermic or exothermic, you should be able to describe at the molecular level what is happening during the reaction. Which bonds are being broken, which bonds are being made, and which side has the greater energy. Below your note is a practice worksheet. Try it out and see.